Hello everyone, welcome back to my channel. In this lecture, we are going to start a very interesting topic in mechanics, which is collisions. Whenever two objects hit each other, something happens in a very short amount of time. For example, a cricket ball hitting a bat, two billiards ball colliding, or a car accident. But the interesting question is what actually happens during that tiny instead of collisions. In this lecture, we are going to understand two most important ideas, which is elastic collisions and inelastic collisions. And most importantly, we will see how momentum and energy behave during a collision. So let's begin. Now, look at this picture. A ball of mass 45 gram is hitting the club. The entire collision happened in only about 3 milliseconds. That is incredibly fast. But even during this tiny interval, several things are happening. First, the ball is moving towards the club. When the club hits the ball gets compressed or deformed, as you can see here. Some portion of the ball is compressed and some kind of deformation happen over here. Its kinetic energy, which is associated with the velocity of this ball, is converted temporarily into the elastic potential energy. Then the ball returns to its original shape. That stored energy is converted back into this kinetic energy. So we can think the process like this. First, we have a kinetic energy of this ball due to its velocity. Then it is converted into the elastic potential energy. And then it is converted again the same kinetic energy as it has initial. So we can say it is in elastic collision happen over here. Okay. And there is a one another important point here is the club exerts the force on the ball according to the Newton's third law. So try to remember the what is the Newton's third law. So we have two bodies like this ball and this club. So the ball is exerts some kind of force. Let's suppose if we can say F1, and at the same time or the same moment this club is also exerting some force on this ball, as let's suppose say F2, and we can say by the Newton's third law, this the magnitude of these two forces should be same or must be same, and the direction which is opposite to each other. And this forces acting on the two different objects. Here we have in this example we have a one ball and another one is a club. So even though the collision happens extremely quickly, physics is still following very strict laws. Now we come to one of the most important laws in collision physics, which is linear momentum is conserved in an isolated system. So here I consider one isolated system. In every isolated system, linear momentum is always conserved. This is the thumb rule you can say. Okay. So if two objects collide each other, then the total initial momentum is equals to total final momentum. Okay. This is the thumb rule of the collision. So students, remember this very carefully. The conservation of momentum applies to collision whether they are elastic or inelastic. So you do not bother about whether the collision is elastic or inelastic. You can apply this rule in both situation if collision is elastic or the collision is inelastic. And we have know what is the formula of momentum here is mass into velocity. Okay, and this holds true regardless of the type of the collision. So even if energy changes, yeah, it may be energy is not constant over here in some processes, but momentum can still remain conserved. So this distinction between the momentum and the energy. So let's understand detail in the next. So now you may ask, if momentum is conserved, what happens to the kinetic energy? So here we need to make an important distinction. The total energy of the universe is always constant. Means let's suppose the total energy E is always constant. I think you know there are many forms of the energy like sound energy, heat energy, potential energy, kinetic energy. These are the forms of the energies. Okay, I hope you know. But the kinetic energy, the energy associated with the motion, okay, can behave differently during the collisions, some type of collisions. So there are two possibilities over here. They are first one is elastic case, and the second one is inelastic case. So in elastic case, we have a momentum is always conserved, okay, P always conserved. And in the elastic one, we have another condition which is kinetic energy also conserved. But in inelastic collisions, we do not have kinetic energy conserved. So the initial kinetic energy is not equal to the final kinetic energy. So don't say that the energy is destroyed because we have considered over here one form of the energy means kinetic energy, and we have another type of energy as well like heat, sound wave, potential energies like this. So this is one of the important ideas of today's lecture. So what I want to convince you that the what happens in the collisions we have to consider concerned about the momentum, and we already know the momentum is always conserved in any type of collisions. But kinetic energy, when we talk about the kinetic energy, it may or may not be conserved in the reactions or collisions. In the elastic, they are conserved, but in inelastic, they are not conserved. So let's first understand the elastic collisions. So imagine two objects approaching each other like this way. This object is going this way and this one. They are approaching each other. So then you can then collisions occur and then they are finally separate to each other. That this is a particle one, this is a particle two, and this is the particle one after the collisions. Okay. Now that we know the in the elastic collisions, the kinetic energy is constant. So I can write like this: the total kinetic energy is equals to total kinetic energy. This is for the final or after the collisions, and you can say this is the before. Okay, and this is the after. I would say here. Okay, here I write the total kinetic energy. That means we have two particles. Let's suppose this is the u1. One particle has a speed u1 and another one has speed of u2. This is the initial speed. Okay, and you know the kinetic energy is associated with the motion of the particle or the velocity of the particle. And the final velocities of these particles is v1 and v2. Now, I don't say this, it must be true. No, it's not. We have to do, I want you to understand this not hold. If I say that 1 by 2 u1 square into m1 plus 1 by 2 u2 m2 square and v1 square plus 1 by 2 m2 v2 square. So it doesn't mean that u1 is equal to v1. It may true or it may be not true. Okay, but this condition fulfilled in every elastic collisions. Okay, so this is a mathematical formula. Okay, but what happens physically? So during the collisions, the object may temporarily deform. So kinetic energy is restored as the elastic potential energy, as we have seen with the ball and the club example, and then it convert and get some original uh, size or volume, as we can see here. The ball after getting the collide, they cover same volume. Okay, and then there's no loss of any energy of the kinetic energy. Okay, I'm strictly concerned about the kinetic energy over here, not the total energy. Okay, not the total one. We have concerned only in the kinetic energy over here. So perfectly elastic collisions are most closely associated with the idealized system. So what such as molecules, atoms, and approximately with some situations involving the balls. In that case, we take as a the same mass after same volume, you would say. Same volume and same mass, they remain the same after collision and the before collision. So we take as a molecules, atoms, and the some kind of balls. They didn't lose their originality. Okay. One more thing here is kinetic energy is a scalar quantity. So you just didn't bother or are concerned about the direction. You just have to add the velocity only. Okay. So if there are some problems, they give you in a two dimension. So you don't need to the resolve any vectors. Okay. So you have to just add like scalar quantities. Okay. So this is the again the distinction between the momentum. In the momentum, we have a we have to resolve the momentum in x direction, y direction, or if they given a problem in 3D world, so we have to resolve in the third component as well. So in this, the kinetic energy equation is simpler, or you can say not complicated than this momentum equation. So we will solve in the problems and you will get comfortable with it after doing some examples. So now we conclude our elastic collision. So in elastic collisions, we know the momentum is conserved, kinetic energy is also conserved, and one more thing, which is very useful in when you solve some problems on exercise. So that means in perfect elastic collisions, the relative speed of the approach is exactly equal to the relative speed of the separation. Here, I have shown two molecules or two objects, A and object B, is approaching each other with speed of u1. Object A has speed u1 and B has u2. Now we know the relativity concept of the speed means they are approaching each other, means they are on the opposite direction. So we have the relative speed of these two objects is u1 plus u2. Here I write over here. After the collisions, they reverse the direction, their direction. Means object A is going this direction. okay, and with velocity of v1, and the object B is going this direction, which is velocity v2. Again, they are in the opposite direction. So we have to just add to get the relative speed of this system. Okay, and after the collisions, we have a v1 plus v2. This is the relative velocity. Keep in your mind, okay? It's not individual velocity of the object A and B. This is the relative velocity before and the after collision. Okay, so in the elastic collisions, we have a three important topic to consider over here. Momentum is conserved, energy is conserved, and then we have a one more formula which is very important when you solve some problems regarding the elastic collisions, which is this: the initial relative velocity is equals to the final relative velocity of this object. We understand the inelastic collisions. Here, the situation is different from the elastic collisions. Kinetic energy is not conserved over here. Okay, but be careful. I am saying kinetic energy is not conserved. I'm not saying the total energy is not conserved. Total energy is conserved always. Means always when whether it is elastic or inelastic. So it doesn't mean the energy disappears. Okay. Instead of kinetic energy is transformed to another forms. As we discussed earlier, there are many types of energies. Okay, heat, sound, potential energy, or there are many others. So when two objects collide and deform permanently, some of the energy goes into the producing that deformation. As you can see here, this clay is hitting on the surface and some kind of deformation happen over here. So we will discuss what is going on here. So a very simple example is modeling K. If you can see here, if you put on some hit some solid surface, it will look like this after the hitting the surface. So this is a kind of a permanent deformation. It will not bounce back like a ball does. Okay, as we have seen already. So this is not perfectly elastic. So it should be your it's has some kinetic energy because initially it has some speed, okay, like v, and then after hitting this surface, it has a kinetic energy goes to zero immediately. Now this energy associated with this clay, where does it go? It should be transformed some another type of energy forms, as we discussed. Okay. Now, students, you want to curious about kinetic energy is not conserved. So where does it go? You might thinking the law of physics broken. But this is not what you are thinking. The energy has simply changed form. Okay. Some energy become a thermal energy, like it is going to some kind of heat. It generates some heat. Okay. So whenever you see the electric components after taking so much um, running, okay, and they emit some heat, okay, it is one kind of loss of energy. So another thing is that acoustic energy, like as I say, sound energy. So the clay hitting on the surface and you may heard some kind of sound, okay. So the kinetic energy is going converted some part into sound energy as well. So some energy can be used to produce permanent deformation of the object. Now, the total energy is conserved, but the kinetic energy is not conserved. Here, we have considered all the forms of energy, and here we consider only kinetic energy. The first, we have kinetic energy is some kind of non-zero value, but after the collisions, kinetic energy goes to zero immediately. So we didn't say the kinetic energy is initial is equals to kinetic energy of the final. It's not the same in this particular case. In every inelastic collisions, as we discuss the types of collisions, elastic and inelastic. Here I draw the table of which quantity are conserved in which type of collisions. So momentum, it is conserved all the time. Okay. Total energy conserved, yes, all the time. But whenever you talk about kinetic energy, this is a red flag in inelastic. Okay. And yes, inelastic. And what is the example of here that the ideal gas atoms or snooker balls and inelastic, the car crashes and dropping a modeling clay. So remember this table. Okay, whenever we have to deal with some kind of examples, and they given us that this is the elastic collision and this is the inelastic collisions. We have these conditions to fulfill. Okay, okay. And by this condition, we got the answer in our questions. Okay. We will discuss in the question part. The 1D collisions are very simple to solve or understand. But whenever we deal with 2D motion, but in elastic or whether it elastic or inelastic, the kinetic energy conservation we easily apply because it is the scalar quantity. Okay. But for the momentum conservation, we have to first decode or resolve the vector in x direction and the y direction. And then we have to compare it. Why momentum is conserved in every particular direction, which is x component of initial, that like this initial, and the x component of the final momentum is same. And at the same time, we have y component of initial momentum and the y component of the final momentum is same, and it is uh, satisfy these equations simultaneously. So how we resolve those equations. So here I consider one problem, which is one particle is going some initial velocity u and having some mass m, and then it collide with a particle which is at rest first, and then they are after the collisions they are one particle is going on this direction, another one is going this direction. So first, conservation of momentum in x direction. First, we have a formula of momentum is p is equals to mv. So initial momentum, the, this particle has no momentum because it is at rest before the collision. So v is zero for this particle, but we have a this momentum of this particle. This is mu, the initial one, and then let's suppose there's a the deflect. It is phi angle and this is the beta angle. So we are considering with the x direction. So we have to take these components only. And we know how to resolve this vector. So this value of mv1 into this component, this cos phi, plus this also component, this is mv2 cos beta. Okay. And this equals to mu. Here I write. Okay. So this is about the x-axis momentum, x component of the momentum. Now we have to consider y direction as well. So in the y direction momentum, first we know this is the at rest is zero. But in this case, in the particular y-axis case, the this particle has a velocity in only the x direction. So we didn't have the component of the y direction velocity. So it means py of this particle is zero. Here I write zero. Now this particle. has this direction, and this particle has a component like this. And this is the value about mv1 into sine phi in the positive x y direction. And this direction has negative y direction. And this is mv2 sine beta. Here, this and this, they are opposite. So here, why we have a negative direction. So I hope you get this point. Why we have a minus over here, this is a plus over here. Because in x-axis, they are in the same direction. But in the component y, y components are in opposite directions. And the kinetic energy is very simple because this particle has zero velocity, means zero kinetic energy. And this is some energy u, velocity u means associated with the kinetic energy one half mu square. And this is very simple, okay? Here, very important historic questions. Suppose I drop a lump of K, it hits the floor and stops. It appears that the clay's momentum has disappeared. Means Ke initial has some non-zero value, but Ke of final part of clay is zero. So in this case, we have a inelastic collision, but we are wrong. Here, you might think that this kind of process violate the conservation of momentum. No, you are thinking in a wrong way. The key here is isolated system. Whenever the clay is going on the earth or any surface, the earth gravity acting on it. So for that, you have to understand you need isolated system means you have to consider earth as well. So if you consider only the clay, the system is not isolated because the earth is interacting with it through a gravity and the floor provides an external interactions. So consider the clay system, clay plus earth. Okay. When the clay moves downward, the earth receives an equal and opposite momentum change. The earth's motion is extremely tiny because earth has enormous mass, but it has not exactly zero. Therefore, we can consider the complete system. Total momentum remains constant or conserved. Sometimes conservation laws become clear only when we choose correct system. Okay. Thank you for watching. Subscribe for more physics lectures.